In this video, we will learn about two-step techniques, which is a class of PU learning algorithms that's particularly suitable for problems with separable classes. The two-step techniques are a class for learning from positive and unlabeled data. So for learning from this kind of data where you have positive and negative examples, but you cannot know their class because they're unlabeled, only a subset of the positive examples gets a label. So the goal is to learn a classifier from this kind of data that looks like this, that can distinguish the positive from the negative examples. The general idea is that there are two steps. In the first step, we are going to identify reliable negative examples in this kind of data. And the second step is that we will train a classifier using semi-supervised techniques so that they can use the labels. Let's look at the output of the first step. So in the first step, we're going to identify some reliable negative examples. So because all of the positive examples are here to the right and maybe more at the top than at the bottom, let's say that the reliable negative examples are here below in the corner of the left side. Using this data then as input, we can use a traditional machine learning technique like supervised or semi-supervised learning to train a classifier from this kind of data, and then we would get this classifier. But note that actually quite a lot of machine learning techniques work iteratively, so instead of having the one classifier, we might actually end up with several possibilities. So in an early iteration, we could get a classifier that looks like this, but then when it gets updated, it looks like that, and maybe later on it looks like this, before it finally looks like this. So actually, there's often a third step in this class of techniques. It's a third step, and it's to select the best classifier from all the possibilities that we had during the training phase. Over the years, a lot of two-step techniques were developed. So here's a list of them, and they all have a technique for step 1, for step 2, and some of them also have a third step. All of these papers chose to publish a combination of the 3 steps, but actually you can mix and match these algorithms for step 1, step 2, and step 3 as you wish. So instead of going over entire papers, I will just go over the main insights for each of the steps. And then when you would like to apply this, I think it's best that keeping your application in mind, you just choose the best instantiations of steps for your application. So the first step is to identify reliable negative examples. To do this, we are going to base this on the smoothness assumption, which means that examples which are similar are much more likely to belong to the same class. So to identify the reliable negative examples, we are going to look at examples that are very dissimilar from all of the positively labeled examples in our dataset. We can select those very dissimilar examples directly based on a distance metric, where, of course, it's very important to choose a distance metric that would make sense in your application. Because many of the two-step techniques that have been proposed in the past are based on, were developed for text. A commonly used distance metric here was the TF-IDF distance. So the term frequency, inverse document frequency. Now, this is specifically a good metric for text, but it might not be useful in other applications. Another commonly used method is to train a non-traditional classifier and use its probabilities for the distance. So remember that a non-traditional classifier is a classifier that aims to predict the probability that an example is labeled. So a traditional one would predict that the class is positive. This one predicts whether an example is labeled or not. And this is something that we can learn directly from the positive and unlabeled data. So the idea here is that any example that has a very low probability to be labeled is probably negative, because that's a reason for having a low probability to be labeled. One additional problem is the question how far or how dissimilar is dissimilar enough to decide that something is reliably negative. Next, I will show you a distance metric that was specifically designed for PU learning. Then I will show you in more detail how this non-traditional classifier works. And then finally, I will show one solution to this problem, how to decide which examples are different enough. So one technique that was specifically developed for PU learning to find reliable negative examples is the 1DNF technique. So this one is based on finding strong positive features first. So a strong positive feature is a feature that occurs much more frequently in the labeled data than in the unlabeled data. So let's look at this for a second. We can define a strong positive feature based on the repayment period, for example, that we can say everything that has a repayment period larger than this value is a strong positive feature. Now, why would we say this? Well, for this feature, we have a frequency of 5 out of 5 of it occurring for the labeled examples. So clearly it's strong there, but it should not be strong for the unlabeled ones. And there we see we have 1, 2, 3, 4, 5, 6, 7. It occurs 7 out of the 18 unlabeled examples. So here it occurs for lesser than half of the examples, while for the labeled ones it occurs for all of them. So this is a strong positive feature. Another strong positive feature that we could find is based on the job security. It would be everything higher than this value. So all of these examples have this feature. So here we would have 4 out of 5 of the labeled examples actually have this feature, while it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 out of 18. So only half of them of the unlabeled one have this feature. So now that we have two strong positive features, we can find reliable negative examples as the examples without any strong positive features at all. So the remaining examples that are strongly negative are the ones that fall outside of these two boxes. So this will be a strongly negative one, this one, this one, this one, and this one. So now using this 1DNF technique, we found all of the reliable negative examples. And then starting from these, we can train a classifier. Let's look at a second method to find the reliable negative examples. This one is based on a non-traditional classifier. Remember, the non-traditional classifier is trained based on the labeled and unlabeled data. And here, instead of the decision boundary, we're actually interested in the probabilities that it will predict, the probability for an example being labeled. So those probabilities will go in this case in this direction. The more in the direction of the labeled examples, the higher the probability, while in the regions of space with fewer labeled examples, the probability will be low. We can then find the reliable negative examples by looking at this lower probability region. So one way to do this is to just define a threshold. Everything with a probability lower than this point is reliably negative. So this would be by finding a perpendicular line on the probabilities. Now these 4 examples would be labeled as reliably negative. Instead of drawing this, choosing this probability, this threshold probability, this can be quite a hard task. You can also say, okay, let's just take the examples with the lowest probabilities, and let's say just the same amount of positive examples that we have. So we have 4 labeled positive, so let's take 5 labeled negative, so also include this one additionally. The one remaining question is which class of classifiers would you use? And this just depends on your application. If you have an application where you think that naive Bayes will work well, then use naive Bayes. If you have a classification where you think logistic regression would work well, use logistic regression. Or any other classifier, of course. Let's now look at another way for setting this threshold for the non-traditional classifier. This is called the SPY method. The reason is because next to our usual PU dataset, we keep part of the labeled examples separately, and these are called the SPYs. So when we train our non-traditional classifier, we will not be using these three labeled examples. But once we have our non-traditional classifier, we will look at the probabilities that these three examples get. So this one will get the lowest probability, and therefore it will decide our threshold probability. So this probability will be here on the line. So then it defines our threshold like this. All of the examples on this side are now going to be reliable negatives. This method has actually the issue that this might not be the positive example with the exact lowest probability. So often you might still choose to go like a little bit lower just to be certain. But it gives you an idea of where more or less the decision boundary will be. So it's useful to use these spies. Of course, to enable using these spies, you actually need enough labels in the data, that you still have enough labels to first learn your traditional classifier from, and then also secondly, that you have enough labels in your spies so that one of them will likely have a low probability. Let's look at step 2. Here we are training a classifier based on the labeled positive examples and the reliable negative examples. Optionally, we can also use the leftover unlabeled examples and use semi-supervised techniques. A type of classifier that is very often used for two-step technique is the SVM classifier. The reason why support vector machines are so popular for this task is because support vector machine handle separable classes really well. And of course, we can use the linear kernel, but also any other kernel, so that the separability doesn't need to be linear. Like the RGB kernel is very flexible, for instance. Of course, if you know that a specific classifier is expected to perform well for your application, then you can just use that specific classifier. So these were examples of supervised methods, but you can just turn them into semi-supervised methods by applying expectation maximization on top of them. Expectation maximization will iteratively improve your classifier by looking at as which classes the unlabeled examples were classified, and then using those to improve the classifier. How exactly this works is outside of the scope of this tutorial. Next to these traditional semi-supervised and supervised techniques, there also have been developed a couple of methods specifically for this setting. Most importantly is the iterative SVM technique, which we will look at now. Iterative SVM starts by training an SVM classifier using only the reliable negative examples and the labeled positive ones. So in this case, you can expect the classifier to look like this. In the next step, we will label all of the examples that were classified as negative by this classifier as reliable negative examples as well. With these new reliable negative examples, we can retrain a classifier. Now it could look like this. And again, we label the ones that were predicted as negative also as negative. And we retrain the SVM classifier. We continue like this until the classifier doesn't change anymore or some other stop criterion is reached. You can see that the classifier started off being a bit too positive, predicting too many examples as positive, but by adding negative examples in every step, it became more and more balanced. actually until a point that it kind of tipped over and started classifying too many examples as positive, as negative, sorry. So this is actually a typical problem with these iterative methods. That at some point you really have to stop early. So learning until convergence is not the optimal thing to do here, and that's why the third step of actually choosing one of the classifiers was introduced. One more note on this iterative method. You don't have to use SVM here. It was just proposed as an SVM method, but it also works for other classifiers. Let's talk about how to choose a classifier. So the most straightforward thing to do is just take the classifier that was learned in the last iteration, but we just saw that with these iterative methods that was not a great idea, because you could get classifiers like this that actually are just too negative. Like here, even those positive examples were classified as negative by this classifier. You could stop earlier by looking at the recall. Remember, the recall is the probability that a positive example gets labeled as such. And given the scar assumption, you can actually calculate this probability just using the labeled examples. So even though it is the same as the probability of a positive example being labeled as such, you can calculate it as the probability that a labeled example is predicted as positive. Interestingly, the classifiers learned in early iterations will typically have a recall of 1 because the classifiers are too positive. So here we see indeed the decision boundary is too far to the left. It's including a lot of negative examples on the positive side, but the recall is 1 because all of the positive examples were also predicted as positive. Well, on the final classifier, the recall is actually smaller than 1 because some of the positive examples are predicted as negative. So you could select your classifier by taking the last one that had a recall of 1, or if you wanted to have a weaker restriction of separability, you could take a smaller value like 95%. By now, you might be wondering, why don't we just calculate the score of the classifiers on some validation set and choose the best classifier? Well, the reason why we don't do this is because we can usually not calculate the typical scores on PU data. This is an issue that hasn't been addressed that much in the literature, but for one score, there has been found an alternative, and this is the F1 score. The F1 score is a combination of the precision and the recall, and the precision is the probability that an example that was predicted as positive is also positive in reality. So the aim of the F1 score is to get at the same time a high precision and a high recall. This is a very useful score in unbalanced data because where normal accuracy just gives too much attention to the class of which there are most of the examples, the F1 score kind of balances those out. So that's why also for PU learning, where this is often the case, the F1 score is an interesting score. The problem is that although we can calculate the recall in using the labeled data, we cannot do this with the precision. This does not translate. So as an alternative for this, there was looked for a score that has the same goal, and what they came up with was this score. So you can see similarly as the F1 score, it's focusing on a high precision and a high recall. But now the sum of precision and recall, it's replaced by the probability of the class being positive. So this one can actually be translated to this score, its equivalent. And you can see that we calculated using only the recall, which we can calculate using the PU data, and the probability for an example being labeled, which we can also calculate from the labeled from the PU data. This derivation I'm not going to do in this tutorial, but you can find it in the paper or also in our survey paper. The next class of PU learning algorithms will be the class of biased algorithms, of biased learning. In that case, we will consider the unlabeled data as negative, but just put a higher penalty on wrongly classifying positive examples than negative examples during learning, and in the hope that this way we will still get a correct classifier for the PU data in the end. See you there!